I'm going to start out here with a question. And the question is, if I took the sine of 30 and I added the sine of 30, can I just add the two angles together and get the sine of 60? And it's actually pretty easy to check if you know how to find values on a unit circle, or I suppose on a calculator. If you remember, the sine of 30 is 1/2. And of course, this other sine of 30 is also going to be 1/2. And if you think about the unit circle, the sine of 60 is radical 3/2. And I think you can see pretty quickly there, 1/2 plus 1/2 is 1, which is not the same thing as 3 radical 2. So this tells us, no, you can't just add two angle measures together and create a new trig function. Okay, so our question in this video is going to be, if I wanted to add the sine of two angles together, or the cosine of two angles together, how would that actually work? All right, so here's what I'm going to do. This is a unit circle, okay? The unit circle has a radius of 1. And I'm going to create an angle here. I'm going to call this angle alpha. You could call it A if you don't like using Greek letters. And I'm going to have a second angle, and I'm going to call that angle beta. These do not need to be the same measure, okay? But what I'm going to try to figure out is a way to represent the sine of the sum of those two angles, all right? And the way I'm going to do this, first of all, this length along here is going to be 1 because this is a unit circle. I'm actually going to take this diagram and I'm going to kind of box this in. So I'm going to create a segment that goes along here, passes this intersection point here, and actually extends out to the intersection point over here. Okay, and I'm going to box this whole thing in a little rectangle. Okay, that rectangle is going to look kind of like that. It turns out that I can actually create a right angle through here. Maybe it doesn't look like one of my diagrams, but that right there is a right angle. And anyway, as a result, what I'm going to have here is a little diagram with a length of 1 and an alpha angle and a beta angle. And I have some right triangles. There's a right triangle here, there's a right triangle here. This is also going to be a right triangle. And there's a pretty neat little proof that you can find the sine and cosine identities for sums and differences. And we're going to use this little diagram to do that. So I have a much fancier diagram up here that I'm going to switch over to. Okay, it's the same thing. It's that rectangle that I made in the first quadrant. So coming from a unit circle, that length there is going to be 1. That's represented right there. There's our angle alpha, there's our angle beta, all right? And what I'm going to try to do here is I'm going to try to label all of the sides of this in terms of the angle measures that I have, okay? So it may not be clear where I'm going with this right now, but just hang with me. So I'm going to call this side X for the time being, and I'm going to try to label this whole side using beta and maybe this side up here. So if you notice, it's a right triangle. I have an angle, I have an adjacent side, I have a hypotenuse. That's a cosine relationship, okay? I can say the cosine of angle beta is equal to the adjacent side over the hypotenuse, that's x over 1. And I can multiply both sides by 1, and we find out that x is just equal to the cosine of beta. So I'm going to replace the x with a cosine of beta. Because now I'm using my angle measure to represent that side instead of just a random variable I made up, okay? Now, I'm going to try the same kind of thing on this side over here. I'm going to call this side y, okay? And I'm going to cover up that value I just found. I'm going to use the beta and the y and the 1. Notice we have an opposite side and we have a hypotenuse. That is a sine relationship. So I could say that the sine of angle beta is equal to y over 1, which is going to tell me that y is really just the same thing as the sine of angle beta. If I put in that angle measure, I would have the length of side y if this was coming from a unit circle. So I'm going to label that sine of beta, and then I'm going to move on. So I now have all three sides of this right triangle, all right? I can move on to other things. I'm going to come down to this triangle down here, and this is going to be similar, except notice the hypotenuse is no longer 1. The hypotenuse of this triangle is cosine of beta. Okay, so once again, I'm going to try to find this length down here. I'll call this length x. Okay, it's a different x probably than the one that we had before. This is just kind of a junk variable I'm using there. But if we look at this right triangle, the bottom right triangle, we've got an adjacent side and a hypotenuse. That is a cosine relationship. So I could say that the cosine of angle alpha is equal to the adjacent side over the hypotenuse. That's going to be x over cosine of beta, okay? Well, I'd like to replace the x here. I'd like to write this in terms of the angles I have. So I'm going to solve for x in this equation down here. I'm going to multiply both sides by cosine of beta. okay? And that's going to tell me that x is the same thing as the cosine of alpha times the cosine of beta. So I'm going to replace x with that. We're going to have cosine of alpha, cosine of beta here on that side. All right? And we're going to continue that over here. I'm going to call this side y. And again, I'm going to ignore this value here. I'm just going to use y and the cosine of b and the alpha. So we have an opposite side and a hypotenuse. That's a sine relationship. So I know that the sine of alpha would be equal to the opposite side of y over the hypotenuse of cosine of beta. And once again, I want to solve for y. So I'm going to multiply both sides by cosine of beta. And y is going to be the same thing as cosine of beta sine of alpha. So I'm going to write that down. I'm going to write it as sine of alpha cosine of beta, but that replaced y. Okay? And we're going to continue this. Now, we have a little issue here with some angle measures. So it turns out that this is a straight angle right here. And so if I'm trying to label different angles in this diagram, it turns out that this angle is 90 degrees. If you think about it, the sum of the angles in this triangle here is 180. I can take away this angle here, I can take away alpha there, and it leaves me with that angle measure. Okay, so you have that angle measure, a 90-degree angle here, and another angle measure here that would have to add up to 180 degrees. That would make this have to be an angle measure of alpha, okay, to make that straight angle work out with those angle measures. All right, and so I'm going to do the same thing labeling the sides of this triangle here. I'll go here, I'm going to call this side x again, okay? And so now I'm working with this angle alpha in this triangle. I've got the opposite side and the hypotenuse, okay? That is a sine relationship. So I know that the sine of alpha in my diagram is going to be equal to the opposite side of x over the hypotenuse of sine of beta. And if I want to solve for x, I can multiply both sides by sine of beta. Okay, and x is going to be sine of alpha, sine of beta. So I'm going to write down a sine of alpha, sine of beta here. Take out that x. Okay, and we can do the same kind of thing on this other side. I can call this side maybe y. If this is side y, then again, I'm not going to use this side here. I'm going to use the two sides I have. I have angle alpha, I have the sine of beta side, and the y. Y is the adjacent side, sine of b is the hypotenuse. This is a cosine relationship with those. So I can say that cosine of alpha is equal to the adjacent over the hypotenuse. That's y over sine of beta. Multiply both sides by sine of beta to get y by itself. And y is the same thing as sine of beta cosine alpha. Okay, last step here. I've got a pair of alternate interior angles right here with these parallel lines. So this angle measure here will be equal to this angle measure up here. This angle measure here is alpha plus beta, so this angle measure here is also going to be alpha plus beta. Remember, I'm actually trying to come up with trig rules for the sum of two angles, so I would like to have something with an alpha plus beta in it at some point. All right, so once again, I have a hypotenuse of 1. That's kind of nice. I have an adjacent side over here. I'll call this x temporarily. So I have an adjacent side and a hypotenuse. That's a cosine of the angle. It's a cosine of alpha plus beta. So cosine of my angle, cosine of alpha plus beta, is going to be equal to the adjacent over the hypotenuse, which means x is just cosine of alpha plus beta. So take that out. That's cosine of alpha plus beta. And then the final relationship here, we've got an opposite side in the hypotenuse. I could call this x or y or something like that. Y would be equal to, well, you've got an opposite side and a hypotenuse. So we could say that sine of alpha plus beta is equal to y over 1. And that means y is going to be sine of alpha plus beta. Okay, so now I put this entire diagram together, and you're probably sitting here wondering, what in the heck is going on here? Well, there's some very important relationships that are going to come out of this diagram. And here's the key. We know that opposite sides of a rectangle are congruent, right? In other words, this side is going to be equal to this side right here. And this is going to lead us to one of our relationships. Notice here, that's the sine of the sum of two angles. It's got to be equal to these two side lengths added up. So what you can see here is that the sine of alpha plus beta, this whole side length over here, is going to be equal to the sine of alpha cosine of beta plus the sine of beta cosine of alpha, okay? In other words, if I want to find the sine of the sum of two angles, I can just take the sine of one angle, multiply it by the cosine of the other, and then I can add the sine of the second angle times the cosine of the first, and that would give me my value, okay? We'll look at that application in just a minute, but that's one idea. Now, second relationship here. Notice I have a cosine of alpha plus beta, okay? We know that this whole side would be equal to this whole side down here, okay? So if I wanted to write an equation here, I could say that, if you're looking at the diagram there, we could say cosine of alpha plus beta is going to be equal, oh no, I'm sorry, cosine of alpha plus beta plus sine of alpha sine of beta. There's a plus there. Sine of alpha sine of beta would be equal to this whole side down here, which is cosine of alpha cosine of beta. So this plus this would equal this. Okay, so that's going to be cosine of alpha cosine of beta. Well, I'd like a statement for cosine of alpha plus beta by itself. Okay, so I'm going to subtract sine of alpha sine of beta from both sides. And that's going to leave me with a statement just for cosine of alpha plus beta. It's going to be equal to cosine of alpha cosine of beta minus sine of alpha sine of beta. Let's go ahead and write that final equation down. So it turns out here that the cosine of the sum of two angles is going to be equal to the cosine of the first times the cosine of the second minus the sine of the first times the sine of the second. Okay? And we were able to prove both of those using our little diagram. Okay? Now, there's a similar proof for the difference of two angles. I don't think I'm going to show that in this video, but anyway, I'll probably at least give you the diagram so you can try it on your own. But it's similar overall strategy. But anyway, that's where these come from.